Hello everyone. So in the last class we were in the process of converting the Navier-Stokes equations, which are originally in physical space, into wave number space. We are close to finishing this up. What we ended up doing in the last class is we converted the pressure term, the pressure gradient term, as you can see here, I kappa j p hat, into in wave number space, right? This is in wave number space, that it turns out to be kappa j kappa k over kappa squared multiplied by gk. So if you remember, gk hat is this nonlinear term, isn't it? So just to refresh your memory, gk hat is this nonlinear term. As you can see here, it is the Fourier transform of the nonlinear term, which is represented as gj hat of kappa comma t, some arbitrary value, okay, some arbitrary denomination we are giving it. It is basically the Fourier transform of the nonlinear term. That is what goes in here, isn't it? That is a nonlinear term, and as I was saying earlier, this is the pressure gradient term, then the viscous term and the unsteady term, as is written here. Then what we did was we took the divergence of the Navier-Stokes equations. We took the divergence of the Navier-Stokes equations, as you can see here. We took the divergence of the Navier-Stokes equations, and the time-dependent term went to 0 because of the invoking continuity, and the viscous term went to 0, invoking continuity again. This is what would happen in physical space equations as well. Then on the right hand side, you have this pressure gradient term and the I kappa j times gj hat. So what ends up happening is, this is what you get. Kappa squared p hat is I kappa j gj hat. And using that, you can derive an equation for, say, p hat, and then derive an equation for the pressure gradient. So I kappa j p hat would be I kappa j multiplied by this right hand side here, which is how you end up getting kappa j kappa k over kappa squared gk hat. Now this happens to be the g parallel to the wave number vector. So that is what is gj parallel. This is where we were at in last class. So what we are saying is the pressure gradient term balances minus g parallel, isn't it? The pressure gradient term balances minus gj parallel. Obviously, I have written here a minus I kappa j p hat representing minus del p del xj, representing minus del p del xj, because that is the term that is in the Navier-Stokes equations. So I am just writing it like that. However, what you have to understand is the pressure gradient term balances minus gj parallel. Okay, now if you put all those into the Navier-Stokes equations, what do you get? Once you put those, see, your time dependent term is d dt uj hat, your viscous term is nu k squared uj hat, and you had the pressure gradient term, and you had just the nonlinear term, isn't it? Going back, you had the pressure gradient term, which is going to be substituted with this kappa j kappa k over kappa squared times gk hat. That is going to be substituted. So essentially it is gj parallel, and then you have in the nonlinear term is just gj hat. So you have gj parallel minus gj hat, which is gj perpendicular. So that's what we have written here. So it is minus of the Kronecker delta minus kappa j kappa k kappa squared gk hat. So remember, this right here is the nonlinear term, convection, nonlinear convection, and this right here is the pressure gradient. So delta jk, the Kronecker delta jk minus kappa j kappa k over kappa squared, that is the projection tensor, pjk. So I have minus pjk gk hat which we knew earlier was going to be Gj perpendicular, minus Gj perpendicular. Because what we had here was minus of Gk hat, because the convection term is negative on the right hand side, and then you have a minus, isn't it? You have a minus Gk parallel. This is minus Gk perpendicular. So in fact, it is, I should say the index I wrote here is wrong. It is Gj hat minus Gj parallel, which is Gj perpendicular, which is what the Pjk, the projection tensor times Gk hat is. It is minus Gj perpendicular. Negative of that, of course. So you have boiled down the Navier-Stokes equations in wave number space to this simple term, which is duj hat dt plus nu kappa squared uj hat is minus pjk gk hat, or minus Gj perpendicular. Okay, so now let's think about this a little bit. If the convection term was 0, okay, if the convection term was 0, then this projection tensor times gk hat would be 0. So if convection terms are negligible, that can happen when the Reynolds number is very small. You can neglect the convection term. The viscous terms are dominant. And then what you would have is only these two terms. So considering the fact that you have converted a set of PDEs into a set of ODEs, if you neglect the convection term, this is easily solvable. You have an analytical solution here in wave number space, because you have a time dependent ODE, and that's it. A time dependent single order ODE, you have duj dt plus nu k squared uj hat is equal to 0. So it is a time dependent ODE, so it will need an initial condition. So let me repeat. You had the Navier-Stokes equations, which are originally partial differential equations. By converting it into wave number space, what you have done is you have converted it into a set of ODEs. And that is a time dependent first order ODE once you neglect the convection term. That can happen when the Reynolds number is really small. So then you only have the left hand side left. So duj dt plus nu k squared duj hat dt plus nu kappa squared uj hat is equal to 0. So let me just write this clearly. The time dependent term, it is duj hat dt. Isn't it? Now if you solve this with a suitable initial condition u of kappa 0, which is your initial condition, then your u hat of kappa comma t is u hat of kappa comma 0, your initial condition, multiplied by e to the minus nu kappa squared t, just an exponentially decaying function based on an initial condition. So that is the physical significance of this equation. So if not for the convection term, you would just have an exponential decay in wave number space based on the viscosity, if not for a convection term. So then you have an exact solution for u hat of kappa comma t, which is u hat of kappa comma 0 e to the nu kappa squared t. So that's the physical significance of that equation. So it's basically a decaying term, right? It's an exponentially decaying term. So that's what we mean. Thus, in the final period of decay, each Fourier coefficient evolves independently of all other modes, decaying exponentially with time at the rate of nu kappa squared. High wave number modes decay more rapidly than low wave number modes, isn't it? Because it depends on nu kappa squared. So higher the value of kappa, high wave number, higher the value of kappa, the faster the decay. Lower the value of kappa, lower wave numbers, the slower is the decay. So that's that. Now let's look at a little bit more detail into the convection term. So that is your R G J kappa comma T. By definition, it is the Fourier transform of the convection term, sure. And if I use the definition of a Fourier transform operator, what I can get is, since this is a derivative, I can just take I kappa times the Fourier mode of the inside part, isn't it? The Fourier transform of the derivative of a function is I kappa times the Fourier transform of the function itself. That is what I'm doing here. So Fk, as in the Fourier transform operator of del xk of uj uk, would be I kappa k Fk of uj uk. So now I am taking a Fourier transform of this uj uk multiplied by I kappa k, of course. And then now what I do is, so I will write uj as an inverse Fourier transform, because uj is in physical space, uk is in physical space. So I will write uj and uk as inverse Fourier transforms. Then what I have is I kappa k of fk, I kappa k fk of, and then uj I write it as uj kappa prime e to the I kappa prime dot x summed over all kappa prime wave numbers, multiplied by the uk value, which I write it again as uk hat of kappa double prime e to the I kappa double prime dot x summed over all kappa double prime. Alright, now what I'll do is, since I'm taking a Fourier transform of this, the Fourier transform operator can be written as the volume average. If a Fourier transform operator is applied over a function, it is the equivalent of the volume average. By definition, the volume average over that entire cube. And the volume average is in physical space. Since these two are not in physical space, that can come out of the volume average. Then what is left in the volume average is only these exponential functions. And I combine those and I write it as e to the I kappa prime dot, e to the I kappa prime plus kappa double prime dot x. And then I have this additional e to the minus kappa dot x because of the Fourier transform operation. Because that's what the Fourier transform operation does. Then what do I do? So this has come out of the volume average, and then I have these summations as well. Now the volume average of this part here, where I have e to the I kappa prime plus kappa double prime dot x multiplied by e to the minus I kappa dot x. Now if I use the orthonormality property, this part here is equal to 0 if kappa prime plus kappa double prime is equal to kappa. And it is not equal to 0 if, I'm sorry, let me just go back to the orthonormality property just to make sure. The orthonormality property is given here. So it is equal to the Kronecker delta, or 1 or 0, right? If kappa is equal to kappa prime, isn't it? That's the Kronecker delta definition. So it is equal to 1. I'm sorry, I said it is 0. So instead of calling it as 0 and 1, I will just say it is equal to delta or 1 when kappa prime plus kappa double prime is equal to kappa, and it is equal to 0, not equal to, but it is equal to 0 if kappa prime plus kappa double prime is not equal to kappa. Okay, so you just need to consider everything related to 1. So that is why I am writing it as, okay, kappa prime plus kappa double prime. So e to the I kappa prime plus kappa double prime dot x times e to the minus I kappa dot x would be equal to the Kronecker delta kappa prime plus kappa double prime, isn't it? Would be equal to the Kronecker delta. I just wrote it as 1 and 0, of course, because that's the value of Kronecker delta. Now, the Kronecker delta would be equal to 1 if kappa is equal to kappa prime plus kappa double prime. Okay? And it is equal to 0 otherwise. So, if it is equal to 0, this entire expression goes to 0. We don't have to consider that. We only have to consider the situation when it is equal to 1, because only then this term is going to exist. So we just have to consider when it is equal to 1, which is when kappa is equal to kappa prime plus kappa double prime, or kappa double prime is equal to kappa minus kappa prime. And then instead of kappa double prime, I just substitute that. So I have this I kappa k, and then I have this summations over kappa prime and kappa double prime, and then I have uj kappa prime and then uk kappa double prime. Now since kappa double prime is equal to kappa minus kappa prime, I can just write this as summed over all kappa prime, uj of kappa prime and uk hat of kappa minus kappa prime. So instead of the kappa double prime, I am substituting kappa minus kappa prime. So I have this expression simplified, which is only dependent on kappa and kappa prime now, because I have considered the dependency that kappa double prime is equal to kappa minus kappa prime. And that is what I have substituted here. That is why I have the uk hat of kappa minus kappa prime. That is what your convection term boils down to. So that convection term multiplied by the projection tensor is the convection term plus the pressure gradient term. Okay, plus or minus depending on how it shows up in the Navier-Stokes equations. But the pressure gradient term and the convection term together is the projection tensor multiplied by the convection term. See? The projection tensor multiplied by the convection term. And that is what is going to go into the Navier-Stokes equations. So here what I have is, I have this time dependent term plus the viscous term, and then I have I, okay, so I have this I kappa k. Now I'm just changing the dummy index in such a way that now I have I kappa L, because in order to use multiple indices. So this would be I kappa L, Pjk, the projection tensor. Remember, the pressure gradient and the convection term together is the projection tensor multiplied by the convection term. So I have Pjk of kappa hat, and then this expression of uj hat of kappa prime and ul of kappa minus kappa prime. So L is here the dummy index. J is the free index here. Follow me? J is your free index, K and L are dummy indices. The reason why I switched to L is because the projection tensor had already a K index in there. So I switched to L. So now just a little bit of explanation. The LHS involves U hat only at kappa. This ODE here is only for the kappa wave numbers. In contrast, the RHS involves both kappa prime and kappa double prime in such a way that you always have a dependency, in such a way that kappa plus kappa double prime is equal to kappa. Okay, so in fact the contributions of kappa is equal to kappa prime is equal to kappa and kappa double prime is equal to kappa as 0 because of the Kronecker delta thing. So what you have is essentially a wave interaction between wave number triads. What do you mean by wave number triads? You have 3 wave number vectors, kappa, kappa prime and kappa double prime. Yes, there is a dependency. However, there is a wave number triad here. So I have kappa, kappa prime and kappa double prime. That is what makes up the wave number triad. Of course, this dependency is there. So I hope this is clear. So now we are down to the Navier-Stokes equations in wave number space in this form. This right hand side is the pressure gradient plus the convection term together. Left hand side, of course, first term is time dependent term and the second term is the viscous term. Now with that as the setting, let's look at the kinetic energy. So we have the Navier-Stokes equations which were originally PDEs, and now we have the Navier-Stokes equations in wave number space which are now ODEs for the Fourier coefficients. What are the Fourier coefficients? U hat of kappa comma t. Now in order to look at the turbulence in a more statistical manner, it is easier to look at just kinetic energy. So let's say the mean velocity is 0. Let's say you are offsetting the flow in such a way that you are not considering any mean. Fluctuations are what you are interested in. Fluctuations of the small u. So u hat. And of course, according to turbulence, according to the Reynolds decomposition in turbulence, the mean of the fluctuations are also 0. So that means the mean of the Fourier coefficients of the fluctuations are also 0. So the other statistic you need to look at is the covariance, which is ui hat of kappa prime comma t multiplied by uj of kappa comma t. Remember, this is the Fourier mode, this is the covariance of the Fourier coefficients. Covariance of the Fourier coefficients, just like you had uj times uk x minus r, now you have uj of kappa prime and uj hat of kappa. So this is the covariance of the Fourier coefficients. Now these coefficients are of course uncorrelated unless kappa prime is equal to kappa, meaning they have to satisfy the conjugate symmetry. So in that sense, because these coefficients are going to be uncorrelated if kappa prime plus kappa is equal to 0 or kappa prime is equal to minus kappa. In other words, that covariance is going to be 0 unless this kappa prime is equal to minus kappa. So all the covariance is contained in this information. Rij, which is the covariance of kappa comma t, is contained here, which is ui minus kappa comma t and uj hat of kappa comma t. This right here is the complex conjugate. So I'm just writing it as ui star kappa comma t times uj hat of kappa comma t. So I have a complex conjugate ui star multiplied by uj. I hope this is clear. That is your covariance. Now what we are particularly interested in is of course the kinetic energy. And the kinetic energy is half Rii. I there is a dummy index. What is I doing? Okay. So Rii of kappa t. So you are essentially, to calculate the kinetic energy, what you need is the covariance of the same component. You don't want u1 u2. You want u1 u1, which is u1 squared. You want u2 u2, which is u2 squared. You want u3 u3, which is u3 squared. Of course, the half will be there because kinetic energy per unit mass is half u squared. So that is why it would be half Rii. And that, according to the definition of the covariance, is ui star kappa comma t and ui of kappa comma t. So I have ui, not ui uj. And then the turbulent kinetic energy is, we know, is half of ui, mean of that, which means because this right here is dependent on the wave number vector. This right here is dependent on the wave number vector. We want a single value. So we sum it over all the wave numbers. And so that's what this is. We sum it over all the wave numbers, half Rii kappa comma t, or kappa summed over all wave numbers of E hat of kappa comma t. So this is the kinetic energy for each Fourier mode. This is the covariance for each Fourier mode. Okay. And so that if you sum it up over all the wave numbers, you get the kinetic energy. Similarly, the dissipation is obtained by taking 2 nu kappa squared E hat of kappa comma T. This is summed over all wave numbers. So that is your dissipation. So this is your kinetic energy and this is your dissipation. So notice what we have done here. We took the Navier-Stokes equations, we converted into wave number space. And what does that mean? That means we will solve for all the u hats as a function of kappa. When I say all the u hats, I mean at all wave numbers. And so we get u hat as a function of kappa. Once we get u hat, what we are interested in is the kinetic energy. So we start by taking the kinetic energy of each Fourier mode, which is E hat of kappa comma T. And that is given by this expression is here, isn't it? Half of ui star of kappa comma T times ui of kappa comma T. We are taking ui and ui, not ui and uj. Okay, we want of the same component. And if you want to calculate the turbulent kinetic energy, you just sum it up over all the wave numbers. That will give you one single value of the kinetic energy in the entire domain, and that is what this is. Similarly, you can calculate dissipation as well. So that ends this module where we have looked at the scales, especially in terms of wave numbers. We looked at the Navier-Stokes equations in terms of wave numbers, the kinetic energy, and eventually the dissipation. And we got one value in there by summing it up over all the wave numbers. We look at this in more detail by looking at things like the velocity spectrum tensor and the kinetic energy spectrum as well. Okay, so we will try to go into more detail into this wave number dependencies of different functions. Thank you.